This research paper explores the fine-tuning of transformer architectures for semantic textual similarity tasks, focusing on the Semantic Textual Similarity Benchmark dataset. The authors utilize various transformer models such as BERT, RoBERTa, and BERT v3, which are pre-trained using different pre-training techniques. These models are fine-tuned partially and then end-to-end, with their outputs combined and used as inputs for gradient boosting algorithms. Handcrafted features that model structure instead of semantics are also incorporated into the boosting algorithms. The paper presents related work in the field, including the use of transformer architectures and boosting algorithms in deep learning. It discusses the development of new algorithms like XGBoost and LightGBM, which offer techniques such as sparsity awareness, weighted quantile sketch for approximate tree learning, and gradient-based one-side sampling, GAUS, and exclusive feature bundling, EFB. The experimental setup includes the use of the Semantic Textual Similarity Benchmark dataset, which consists of English datasets from various sources like image captions, news headlines, and user forums. The dataset contains 5,749 examples in the trained split, 1,500 in the dev split, and 1,379 in the test splits. The task is treated as a regression task, with given labels in the 0-5 range. The metrics used for this task are Pearson's correlation coefficient and Spearman's rank correlation coefficient. The paper also provides an error analysis, focusing on the edges of the prediction range. It details the hyperparameters chosen for the final models using mean-squared error and cross-entropy error. The results achieved by transformer architectures and boosting algorithms are presented, and the authors discuss and analyze these results, exploring different data splits to obtain more consistent results. Finally, the paper concludes with suggestions for future improvements. The paper presents a comparative analysis of various transformer models and their performance on the STSB dataset, focusing on sentence similarity tasks. It explores two different fine-tuning approaches: partial fine-tuning with a frozen base model followed by end-to-end fine-tuning. The results indicate that transformer models outperform baseline models, with BERT v3 base achieving the best results in partial fine-tuning and BERT v3 large and end-to-end fine-tuning. The study also applies boosting algorithms to enhance the performance of these models. LightGBM and XGBoost show better results compared to AdaBoost, with LightGBM performing slightly better in most cases. Interestingly, the hyperparameter optimization procedure consistently selects combinations of different transformer architectures rather than combining smaller and larger models of the same architecture. This suggests that different architectures excel on different examples. The paper also highlights the importance of handcrafted features, such as counts of characters, stop words, tokens, verbs, adjectives, overlapping tokens, and overlapping lemmas, which are used as inputs for the boosting algorithms. These features provide additional information about sentence structure and semantics, helping the boosting algorithm to understand the sentences better and make more accurate predictions. The research explores the combination of modern transformer architectures, such as BERT, with traditional ensembling algorithms. It examines the performance of ensembling outputs from multiple transformer architectures and handcrafted features. The study suggests that this combination achieves higher metric values on the development set but is detrimental to performance on the test set. The issue might be due to predefined dataset splits. To address this, the authors retrain the best ensemble model using a stratified cross-validation split, which shows better generalization properties on the test set. The analysis of the best-performing ensemble models indicates that the number of meaningful lemmas is a good indicator of whether an example is difficult and that the models are less accurate on the edges of the prediction range. This work serves as a starting point for further ideas, such as investigating the effect of ensembling with small transformer models or extending this idea to sentence embedding models.